This is lesson 4 in the capacitance topic. Today we're looking at discharging a capacitor. It's going to be quite hard and quite a lot of maths. Make sure you watch the other video showing you the worked examples we're going to go through. These are the spec points for the lesson, but these ones here are ones we're going to go through in some PAG work in school rather than now. So first up, I'm going to make an analogy with a bike pump. I want you to imagine your bike pump is full of air. You pumped it up to the max, it's full of air, and then you press the valve to let the air out. At first, the air rushes out really, really quickly, and then after a while the air still comes out, but it's a bit slower, it's not quite coming out as quickly. Just keep that analogy in mind as we go through looking at what happens to a capacitor. So here I've got a circuit. It might look a bit complicated, but let's walk through it. Here I've got a power supply with a voltage of V0. Not zero, doesn't mean it's actually 0 volts, we're just calling it V0. This is a switch. This is a capacitor, this is a resistor, and this is a voltmeter. Now, when I've got this switch closed, then I've got current flowing around the circuit, and that charges up my capacitor. So as electrons are leaving the negative end of my terminal, they'll be coming around here and going onto the negative end of the capacitor, and they'll be drawn off of this part of the capacitor and pulled towards the positive end of the power supply. So I will end up charging up my capacitor. My capacitor will become charged, and the longer I leave that switch closed, the more charged it becomes. So what will eventually happen is I will eventually have charged up my capacitor until it has got as much voltage as the power supply does. We're going to leave going into too much detail there, and we'll do charging next lesson. Today we're going to focus on discharging. And to discharge the capacitor, I now need to open the switch. So when I open that switch, basically this whole section is just completely disregarded. This doesn't do anything anymore because it's not connected. And now I'm just looking at this bit of the circuit here. Just this bit, once the switch is open. And when the switch is open, what will happen is the capacitor will discharge, which means the charge leaves the capacitor. Now what that means is that this part of the capacitor here, where I've got lots of negative charge, will push electrons off of it. If I've got loads and loads of electrons here, they're going to repel each other, and the only way they can repel each other to move is around the circuit and through the resistor. So I start to get a current of electrons. My negative charge moves around this way, through the resistor, back up through here, and onto the positive plate. And as the negative electrons leave the negative plate becomes closer to neutral. And as the electrons move around and come back to the positive plate is becoming closer and closer to neutral. So what's happening is as the electrons leave the negative plate and come round to the positive plate, they neutralize. And this will keep on happening until the entire plate becomes neutral. And when the charge is no longer on the capacitor, when the capacitor no longer stores any charge, then the current stops. Now, at the very beginning, I had loads of negative charge on here, which means the electrons were initially pushed off very, very quickly. So at the beginning, I had a very high current because the electrons were being pushed off so quickly, a bit like our bike pump. When we opened the bike, or the bike tyre, when we let the air out at first, the air rushed out really quickly, but towards the end it slowed down. Same thing here. At the beginning, the electrons are pushed off really quickly, and there's a very high current through the resistor. But over time, as this becomes closer and closer to neutral, the electrons only move off very slowly. So over time, the current very slowly decreases until it reaches 0 eventually. The same thing happens with charge and voltage. So the current decreases down to 0, the voltage decreases down to 0, and eventually the charge decreases down to 0. This is what the graphs look like for all of them. So at the beginning, this is once we've already charged the capacitor. So at 0 time, we've got a fully charged capacitor. It's got all of its charge on it. So you can see it's got all of its charge on at the beginning. So at t equals 0, that is the time at which I just open the switch. So the current starts to flow through the resistor, being pushed around by the capacitor. But as the capacitor loses its charge, as the electrons move from the negative to the positive plate, and it becomes more and more neutral, the charge decreases, and because of that, the current is going down, and also the voltage is going down. This is exponential decay. This is an exponential curve. And the equations to describe it are a bit more complicated. They're probably the most complicated equations we do in A-level physics, and they are these. So the voltage follows this equation, the current follows this equation, and the charge follows this equation. T is time. V0 is the initial voltage. Now the initial voltage is sort of like the maximum voltage, same thing for current and charge. So V0, I0, and Q0 are the initial voltages, the initial current, and the initial charge. C is the capacitance, and R is the resistance in the circuit. And V here, V would represent the voltage at any specific time. So when T is 0, then V would equal V0. You can try that. When T is equal to 0, then e to the power of minus 0, that's just 1, so V equals V0. If I put in 10 seconds here, so if into this equation I put t equals 10 and I put a 10 in there, then when I put in all the other numbers, it would tell me what the voltage was after 10 seconds. Likewise, if I put 15 in for t there, so after 15 seconds, I would then equal what the current is after 15 seconds, so on and so on. Now, where this can get complicated is that you don't get given these equations in your formula booklet. But before you freak out and think you have to memorize them, you don't quite have to memorize them either. It's sort of a halfway. What you get given in your formula booklet is this for capacitors. Now, you'll notice that this looks very similar to these. In fact, it's the same, but instead of V's and I's and Q's, it's just an X. It's X and X0. What you have to remember is which ones to use. We haven't used this one yet, but we're going to use this one in the lessons next week for charging. But beware, it's not as simple as just these being the discharging one, these being the charging ones. The way you should try and remember it is that whenever we discharge a capacitor, current, voltage, and charge all decrease. And this equation here is for decreasing values. This equation here is for increasing values, and we'll look at it next week. So what you have to remember is that whenever you discharge a capacitor, the voltage, the current, the charge all decrease, which means you use the decreasing version of the equation. You'll notice there's another equation here. We're going to look at that one now. This symbol here is called tau, and it's the time constant. So what we've got is we've got our current, and our current decreases with time. We can see that on the graph, and we can see that from the equation. So we can see that as time increases, the current I in the circuit decreases exponentially. This term here, CR, this is called the time constant. It's written with the symbol T, or not T, it's called tau, T-A-U, it's a Greek symbol. It's sort of like a lowercase t but without the top on it. And the definition for the time constant is it's the time required to discharge the capacitor to 37%. So we allow either the voltage or the current or the charge to go from its maximum value to 37% of that maximum value. Now that might seem a little bit random, why 37%? We're going to have a look at that now. So let's take the current equation. I at a certain time equals the initial current times e to the power of minus t over capacitance times resistance. Well, let's change t to be the time constant. And the time constant, we just said here, is equal to CR. So if the time we're looking at is equal to CR, and rather interestingly, if you do the units of C times the units of R, it gives you seconds. So if we say that the time is equal to some number that is the same thing as the capacitance times the resistance, then the term in the power up here becomes CR over CR, which is 1. So we get I equals I0 e to the minus 1. Well, if you put into your calculator e to the minus 1, which is the same thing as doing 1 divided by e, you get 0.37. So when t is equal to whatever c times r is equal to, the current at that point will be 37% of its initial current. We can also think about the halving time. Now this is something that's not necessarily in the spec. It's not very clearly in the spec, and you won't find it in the textbook either. But it is something that they might ask you about. It's something that they might do. They might give you a little bit of information in the paper there and then and expect you to answer an exam question on it. So it's worth practicing now in case they do something like that. The halving time is the time it takes for the current to reach half of its value. It's a bit like the half-life in radioactivity that you would have done in Key Stage 4 in GCSE. It's the time it takes for the current to go to half of its original value, where the time constant instead is the time for it to go to 37% of its original value. To get the halving time, all you do is you just do CR times ln2, ln being the logarithm with a base of e. So the halving time is just equal to the time constant times ln2. So the halving time would be the time for the current to fall to here. So this is half. So that would be that time. The time constant would be for this to go to 37% of its original value. So that would be about here. So that would be the time constant. So hopefully you can see some of the similarities I was talking about there between discharging a capacitor and discharging the air out of a bike tyre. The charge rushes off of a capacitor very quickly at the start, and then it slowly decreases with time, so that it follows this graph. The same thing happens with air out of a bike tyre. The air rushes out of the bike tyre very, very quickly at the beginning, but at the end it sort of very slowly comes out until eventually it stops.